Today I will be talking about wavelets because the future of machine learning is about wavelets and Fourier transform and those things. Because in signal processing is more successful in representing data or signals. They are more successful than even machine learning guys because they represent the signal as a function in function space. But machine learning community doesn't respect function spaces. They do something and they don't know what they have learned. For example, the deep learning doesn't know what it has learned. That's why they created explainable AI and those techniques to understand what they have learned. But that's the result. It's not the cause. You have not avoided. You have not do it in advance. You are just seeing it as a result of your mistake. So that's why wavelets are very important in compressing data, in representing your data in data science. And future, I promise you, in 2031, many of the algorithm in neural networks, if there is still neural networks out there, you will see that it is a wavelet-based neural networks, or wavelet convolutional neural networks, or wavelet transformer methods, and transformers in NLP, I mean. So we have wavelet transformers. But what is a wavelet? We have many. So it's because Fourier transform has its limitations. You cannot, even if you use short time Fourier transform, which is a generalization of Fourier transform, you cannot do time frequency localization very good. That's why people invented wavelets, and for example, Morse wavelet is like this. You have something like this. So it is localized in time. And if you do the Fourier transform of this, you will see it's like a bandpass filter, and it has a central frequency 1.88. Of course, it is in terms of hertz. There are other wavelets. Debussy, for example, Debussy, that woman invented, who got Nobel Prize for that, and invented Debussy wavelet. And we have also bump wavelet. We have also analytic Morlet wavelet. And what we are doing is we will represent this signal, this strange signal. It could be a financial time series or anything. It could be an image, a vectorized image. So you give it to wavelet transform, and it gives you some coefficients. For example, if you do it discrete wavelet transform that I will explain, it's just time and scale. Scale is just the opposite of frequency. So here you see that you have some coefficients here, and then you go to finer and finer scales, and then it becomes even finer here. And so this is you save all of your coefficients in these spaces because it's a discrete. You need discrete amounts. And in continuous wavelet transform, T of A and B, and A is just the scale, which is the opposite of frequency, and B is just a time shift of time. So it's just 1 over square root of A, x of t, psi star of t minus b is the time shift factor, divided by A, which is scaling, and then d of t. But in discrete wavelet transform, we have d of A and b, which is 1 over root of b, m from 0 to p minus 1. So integral is replaced by sigma f of t of m, and then psi of tm minus a over b. And you know, in the dyadic scaling and shifting, we have a signal. I will explain these things, but we have a high pass filter and then low pass filter, and then again high pass filter, low pass filter. So this is level 2, and then your approximation continues. You have again low pass, high pass, and this goes forever. But in practice, 3 level is enough for your brain to understand the picture of your friend's face. And so usually we do in practice 2 or 3 level approximation, and not infinite levels. We don't need to go up to infinity. And there are many applications, for example, wavelet denoising, wavelet denoising. For example, you have images of James Webb Telescope and you should denoise it, you discover something. And so first you perform a multi-level wavelet decomposition. And the second step is identify thresholding techniques. For example, which coefficient do you want to cut? You don't care about that. This is very interesting, because when you do lasso or ISTA, you're just optimizing L1 norm and you do lots of computation. But in thresholding, we just drop it out. We just omit the coefficients that are not very big, or they don't have the good mutual information between your result and the coefficients. And this is what your brain does. Your brain does not solve a compressed sensing optimization problem or ISTA or lasso problem to minimize the L1 norm. It does not do that. It does not do any optimization. It does not do like that artificially. What it can does, they're just bunch of neurons and nothing else. They can understand that, if the activation of it, I will explain it later, why it is important for understanding the human brain. The threshold, and then finally we threshold and reconstruct. There are other applications of wavelet. For example, this is very popular, but maybe it is not the best way. So wavelet scattering of signals and images, financial series, and those things. We use a deep convolutional neural networks, as we do. For example, we have a convolutional layer. We give it to a ReLU. We give it to pooling. So this is just for one layer, and then we repeat this as for example, for 4 layers like this. And your signal, F signal, is convolved with the filter. We get some coefficients. For example, in layer 0, these are the coefficients of wavelet transform. But the thing that occurs is in 2031, we should have algorithms like this. They do abstract harmonic analysis. We do Fourier transform on groups. And then, so you need those abstract harmonic analysis. And if you do it for neural networks and for real data, we call it a branch of computational harmonic analysis that some researchers are actively working on that. They use the concept of symmetry. So, if you transform something it's like a group action. It's like that you can represent it by a group, and then you do Fourier transform on group, and so it will be an active field of research in future. And now many people are working on that, but it is very different from traditional machine learning. And now I want to talk about how can we do discrete wavelet transform. The continuous wavelet transform is like this. W of f of u in s is 1 over square root of s. F of t psi star is conjugate. T minus u over s dt. So it's just the convolution. This is convolution. Convolution of psi s bar of t. And psi is just 1 over square root of s psi of t over s. So these wavelet coefficients are a result of bandpass filtering. Look at that like this. So you have a signal f of t, you give it to a bandpass filter, and yet you get wavelet coefficients. A good example is the dyadic Haar. It is orthonormal. So psi bar of I and n is 2 to the I psi of t minus 2 to the I n over 2 to the I. And you can represent it by this signal. And after doing orthogonality, using orthogonality between scales, it becomes like this, because you're putting all the signals and then this pattern repeats forever. And the reason that discrete wavelet transform is a little bit tricky for you, maybe just because so you have to learn this in order to understand why we are doing this low pass filter, high pass filter, and those things. What is the philosophy behind that? The problem is that we can represent by, for example, this is level 1. This is level 1, high frequency, I is equal to m. And from frequency Fn to frequency Fn over 2. And then the next level, it is the spectrum is half of the original one. So this is the level 2 high frequency, and then even half of that, and then even smaller and smaller. But what about this area? Call it father wavelets, because this is the low pass filter area. And for example, here is Fn over h, Fn over 4, and those things. So you got the idea. We don't know how to. Of course, you have a lot of bases to represent your function space, but every stretch over only covers half remaining bandwidth. So what about the remaining one? And you can solve it with father wavelet. Some people call it scaling function. And we usually in the literature represent it by phi, because the mother wavelet were represented by psi, and father wavelet represented by phi. So, for example, mother wavelet is like this, -1, 1. This is the mother wavelet, and the father wavelet is this. So it's like a low-pass filter phi of t. And father wavelet is a low-pass filter. And what I want to say is you represent the detail of the signal by d of S and U. And so these are your coefficients, x and n, psi of S and U of n. And a of S and U is n from 0 to n minus 1, x of n, phi of S and U of n. So phi is your father wavelet, psi is your mother wavelet, and you are, for example, for mother har, you can represent it as this. Imagine it is a signal of length 2 only, so n is 2, and the corresponding scaling function, the father scaling function, represented by phi, is just this. So this is the low pass, or people call it approximation, because it's just the approximation of that. We don't care about details. But here, the mother wavelet is the detail. It is the high frequency information that is represented, high frequency. And now you understand what is high frequency and low frequency. So this is the approximation, and detailed is D. Now you understand why discrete wavelet transform is a little bit weird. So from now it is not weird, because you understood that this is a high pass filter and low pass filter. And then you downsample it by 2 to reduce it, because it becomes very big, so you need to reduce it. And then it becomes A0N and D0N. But you can continue with this to another level. For example, you give it to another H0 and H1, downsample it, and this continues forever. Not forever, but in practice you do it, as I said, by just 2 or 3 levels, and 2 or 3 levels is enough for your brain to recognize your friend's face. And now I want to talk about maximization of information transmission over noisy channels. You know, reliable communication of information over noisy channel is a widespread issue. It ranges from construction of good error-correcting code to feature extraction. So I of X and Y, so you have input X, you have output Y in a noisy channel, and you want to maximize this mutual information. You know, this is H of Y minus H of Y of. Always think of amount of uncertainty that is reduced. So if this is small, your mutual information is small. And the mutual information is just a nonlinear generalization of that linear correlation that you do in finance or machine learning. But it is the nonlinear version. It represents nonlinear things as well. And the problem is that, of course, so Y is the output, X is the input source. So the problem is that I is intractable, like many problems in machine learning. But it is beautiful that I of X and Y is symmetric. And there are few special cases, but we don't care, because for example, when Y is deterministic and invertible mapping, then you can write H of Y very easily. H of Y is just log of J, and J is the Jacobian. derivative of yi with respect to xj. This is the Jacobian